It is my pleasure to start this last workshop of this program on ancestral lines under selection and recombination, as I already said. And this is joint work with my postdoc, Frederic Alberti, who is also here. And the structure of the talk is simple. I will first explain the selection-recombination differential equation in the usual forward direction of time. And then I will solve it via genealogical thinking. And then I will turn to the dual process. So, what is recombination? Recombination happens when two parents create an offspring that is a mixture of the two. And here is my idealized version. So I start from a pool of germ cells, eggs or sperm, and each of them carries one copy of the genetic material in the form of a sequence of finite length. And then at fertilization, two germ cells meet and start the life of a new organism. And when that organism starts to make its own eggs or sperm, then the two sequences perform one or more such crossover events, and they then relink across, so you get these mixed sequences, and they then separate into the next generation's germ cells and rejoin the pool. I will throughout work at the level of this germ cell pool, and I will identify an individual with a sequence of little n sites collected into a set S. At every site there is a letter, little xi at site I, and it can be 0 or 1. And the sequence of all these letters, little x, is then the type of the individual, and the set of all possible types is the type space capital X. Now, we also need the marginal types. So for a subset U of S, X sub U is simply the subsequence corresponding to the sites in U. And let me first talk about reproduction. So we assume throughout that there is only a single selected site. That's the I bullet here. And all other sites are called neutral sites. And then types that have a 1 at the selected site reproduce at rate 1, and they are called bad or unfit. And those that have a 0 at the selected site reproduce at rate 1 plus S, so they have a selective advantage, and they are called good or fit. And if you wonder why 0 is good, then the reason is German school marks, because there, the smaller the number, the better you are. So, now if we want to talk about recombination, we should first introduce a partial order on the set of sites, and that goes as follows. We say that site I is less or equal site J if it is on the same side as the selected site. No, it's on the same side of the selected site as J, but closer to it. So 7 is less than 8, and 3 is less than 2, and 3 and 7 are incomparable because they are on different sides of this selected site here. And then I collect into a set DI all sites that are greater or equal than I, and we call that site the I tail. And the complement is hi Enrico, and we call hi Luigi, welcome. And we call that, sorry, we call this set the I tail, and the complement is the I head. So here is the 2 tail, the 2 head, the 8 tail, and the 8 head. And note that the selected site is always in the head. And now we can talk about recombination. So we will assume throughout that there is at most one such crossover event. So here we have 2, but we assume that there is at most 1. That's quite a common assumption. And then that means that a recombination event simply makes a split between some head and some tail. And we say that recombination happens at site I if the split is between the I head and the I tail, and we assume that that happens at rate rho I in every individual. More precisely, here is a situation where the last site is the selected one, that's why it has an underscore. And then recombination at site I means that this offspring copies the I head from the blue parent, the Y, and copies the tail from the green parent, the X, and that happens at rate rho I. So far I've been talking about what happens to single individuals. Now let me put up the population model. We have a population of constant size n. By the way, I should say the model is the Moran model with selection and recombination. So we have a population of size capital N. We work in continuous time. Every individual reproduces at a neutral rate 1, and the fit individuals additionally reproduce at the selective rate S. So altogether, the bad ones have only the neutral rate, so reproduce at rate 1, and the good ones have the neutral and the selective rate, so altogether they reproduce at rate 1 plus S, as it's supposed to be. Then when a reproduction event happens, then the parent produces a single offspring, and that inherits the parent's type and replaces a uniformly chosen individual in the population. So this way population size is kept constant. And furthermore, every individual recombines at site I with a randomly chosen partner, and that happens at rate rho I for every site. And then the recombined offspring again replaces a uniformly chosen individual. So that was the model in words, but we are here at a meeting about interacting particle systems, so you expect to see an interacting particle system representation. Here it is. We have n equals 5 individuals. Each is represented by a horizontal line. Time runs from left to right. We have 4 sequence sites. The selected one is number 3, and it is orange, but I wonder whether you can actually see it. Can you see that that is orange? Okay, the colors are quite different from the colors on my screen. Okay, and then 3 things can happen. And the events are represented by certain graphical elements. So first we have neutral reproduction events. They are indicated by these arrows with the normal arrowheads, and they are attached to every line at rate 1. And then the tip picks the line uniformly, and then the arrow means that the individual at the tail places an offspring on that line where the tip is. So this individual places its offspring here and replaces the individual that has been living on the line before. Next we have selective reproduction events. They are indicated by arrows with star-shaped arrowheads. They are attached to every line at rate S, but then the convention is that only the good individuals may use the arrow to place offspring. The bad individuals ignore the arrows. So this individual here at the tail is bad because there is an orange one, so it ignores the arrow, and the individual that has been living on the line before continues. But then next, this individual here is good, so it uses the arrow and places its offspring here. And last but not least, we have the recombination events. They are indicated by squares with a recombination site inscribed. And such a square means that the individual before the square is replaced by an offspring that is pieced together from a randomly chosen head and a randomly chosen tail. So this individual here is combined from the head of this guy and the tail of this guy. Gives this. Okay, so far for the interacting particle representation. What comes next? Yeah. To describe what's going on mathematically, we work with ZTN, that's a counting measure on the type space. ZTN of X is the number of individuals of type X at time t. And then we take the dynamical law of large numbers, that is, we let n to infinity without rescaling any parameters of time. So that limit will be a deterministic one. And in that scaling, the process of relative frequencies will converge to omega t, and omega t is the solution of the selection-recombination differential equation, which I'm going to explain in a minute. So omega t is a probability measure on the type space, and omega t of x is the proportion of individuals of type x at time t. And now to the differential equation. So it has a selection part and a recombination part. And the selection part tells us that type x increases in frequency at rate s if it has a 0 at the selected site. But at the same time, it decreases in frequency whenever it is replaced by the offspring of some good individual. And so that is S times the proportion of the good individuals. And I have this sort of somewhat sloppy shorthand here, that this means the frequency of those guys that have a 0 at the selected site, and no matter what at all other sites. Okay, and then next comes the recombination part. And to explain that, let me go back to the recombination picture and let me rewrite it in a marginalized form. So this way you see that recombination at site I gives you an x whenever the first offspring agrees with x at the sites in the head, and the second offspring, and the second parent agrees with x at the sites in the tail, and all the other sites then don't matter because they are thrown away. And we can even write it shorter in terms of heads and tails. And then you see this corresponds exactly to this product here. So here you have the product of the frequency of parents that have that agree with x at the sites in the head times the parents that agree with x at the sites in the tail, and all the other sites don't matter. And you get the product because parents are supposed to meet randomly. And then also you lose an x all the time because every individual is being replaced by recombined ones all the time as well. So this is my somewhat messy version of the differential equation. It will improve in a minute, but for the moment, let's take it as it is. But let me first think a bit about why this could be interesting. So this differential equation is a classic in the context of what is known as hitchhiking. What does that mean? Well, the neutral sites or neutral letters, they do not themselves carry any selective advantage, but they can inherit the selective advantage of a 0 at a selected site if they appear on the same sequence. So if they are linked to a 0 at a selected site, and then sort of they inherit the selective advantage, that is, they have the increased reproduction rate and can increase in frequency and overgrow the bad ones and so on and so forth. So they can hitchhike along with the selected site. But the differential equation is stubborn. There is a monograph by Ethan Aiken on the geometry of population genetics, and the very first sentence in the book reads, "The differential equations which model the action of selection and recombination are nonlinear equations which are impossible to solve explicitly." So the nonlinearity, of course, comes from that product here. And here we also have products, so that is indeed true. Yeah.
Why do you sum does not include the special site? In the previous slide, in your generator, you are not making recombination in the special site.
Here?
Yeah.
That is simply because, let us go back to the partial order. There can't be any recombination here. There can only be recombination at the links. So that is simply due to the partial order. So it means nothing, basically. But good question. Okay, so let's get back to Ethan Aiken. So, and Ethan Aiken should know, because he's not only the author of this monograph on the geometry of population genetics, but he's also the author of a classic on dynamical systems. Okay, but nevertheless, in 2006, Stefan Song and Langley gave it a try, and they came up with an approximate solution for the special case of 3 sites at the cost of wild approximations and a very technical result in terms of special functions that can only be evaluated numerically. And there is no hope to generalize this to more than 3 sites, and also there is no hope to understand what's really going on in that technical solution. So we started out with a goal to solve the equation for an arbitrary number of sites without an approximation and in a streamlined way that also yields some insight. So I agree that is a mouthful, but let's see how far we get. So it is essential to rewrite the differential equation in a streamlined way. The first thing we need are the marginals. So for a probability measure mu on the type space and a subset U of S, mu sub U is the marginal measure with respect to the sites in U. So for a subsequence XU, mu sub U of XU is simply the probability that a sequence X agrees with the subsequence at the sites in U and has no matter what at all the other sites. And with this we can write down our workhorse. The workhorse is the recombinator. And for a probability measure U on X, the recombinator Ri at site I turns mu into the product of the marginals with respect to the head and the tail. And if you write it out component-wise, then you get this product that you have already seen on the right-hand side of the differential equation. Put differently, Ri of mu is what I like to call the recombined measure. And put differently, that is the distribution of sequences that you get if you piece a sequence together independently from random I heads and I tails. Okay, and this now allows us to streamline the differential equation. So that was my original messy version, written out sort of component-wise. It's much better to formulate it directly at the level of the measure. And you won't be surprised about the recombination part here. So that simply tells us that recombination turns the current population into its recombined version all the time at rate rho I at all the sites I. And then to see the selection part, we define a fitness function capital F that simply decorates mu of X with whether it is good or bad. And then we need the function little f of mu that is simply the proportion of fit individuals in the population. So the proportion of individuals that have a 0 at a selected site. And then you see immediately that this sort of translates. So This is my nice up version. And let us now set out to solve it. I will construct the solution in a recursive way. And to this end, I first define my iteration indices. And I do this by choosing a non-decreasing permutation of the set of sites. And by this I mean the following. I start at the selected site here, and then I move outward. First here, then here, then here, then here, then here, and so on and so forth. Or put differently, I can say I start with a selected site, and then sort of I add sites on either way without leaving any holes. The way to do this is not unique, so you could as well work outwards all the way to the left first and then move outwards all the way to the right first. There are many possibilities. The only thing is you decide this for once and then you fix it. And then we relabel the heads and the tails and the recombination rates accordingly with upper indices. And then we will get a hierarchy of solutions. So omega t0 is the solution of the equation with all recombination rates set to 0. So that's the pure selection equation, no recombination. And then omega k is the solution truncated at k. And with that we mean that we set all recombination rates beyond k to 0. So getting back to this, these iteration indices, it means we start here without any recombination and then we allow recombination first here, then we add recombination here, then here, then here, then here, and so forth. So, and here's the result. This is the solution of the pure selection equation, so the start of the recursion. You are not supposed to read or understand this at this point. It's just here for you to see that it is simple and explicit. And then the solution truncated at k, we get that by a recursion, so as a functional of the previous recursion step. And once more, you are not supposed to read this at this point, and I resist the temptation to try and explain it at this point. Let me just say that initially we guessed this solution with some genealogical hindsight, and our first proof was purely analytical, so just guess it and check it with the help of the properties of the recombinators. But that is not what you want to see, I think. You want to see a solution, you want to see a probabilistic proof and some genealogical meaning, I think. So let's set out to do that. We turn again to the Moran model, this time without the types. And we want to follow back the ancestral line of an individual here at time t, to which we refer as the present. And the standard tool for that is the ancestral selection-recombination graph, or ASRG for short. And that goes as follows. Start here, follow back its line. When it meets a recombination square, then it's clear that sequence splits up into head and tail. When a line meets a neutral arrow, then it follows the arrow back because it comes from this parent. And then when the line meets the tip of a selective arrow, then you don't know what to do because, well, you have already seen who is the true parent of this guy depends on the type of the parent, but you don't know the type yet. So, what is going to happen? Let me explain again what you in principle already know, but it's important, so let me make it explicit. If the individual at the tail of the arrow, we call that the incoming line, if this is good, orange, then it will be the parent of this individual at the tip, regardless of the type of the other line. And if the incoming line is bad, then the continuing line, the one at the tip of the arrow, is the parent, and regardless of its type. And we call this rule the pecking order, and note two things. First, the offspring is bad if and only if both potential parents are bad. And also the incoming line is queried first. So only if the incoming line is bad, the continuing line gets a chance. And both these properties generalize easily to more than two lines. So, to get back to this case, we don't know the parent because we don't have the type, so we follow back both possibilities and we get a branching event. Okay, and then when we have constructed that graph, we again assign types to all the lines in the graph, and we propagate them forward exactly as in the original Moran model, and this gives us the type of the individual today. Now we take the n-to-infinity limit. So recall we took this n-to-infinity limit without rescaling of parameters of time or time. We did that to get the differential equation. So we do exactly the same thing here. And then the graph simplifies because then we don't have any coalescence events anymore. So here we have a coalescence of this line and this line into one. It never happens in that limit. That simplifies this graph. And only two kinds of things can now happen. Namely, every line branches at rate s. And when there is a branching event, we place the incoming line immediately below the continuing line, because that later allows us to query lines from bottom to top in the order of the pecking order. And yeah, we also leave out that star-shaped arrowhead because we don't need it anymore. And then also every line splits at rate rho I for every side I. And when that happens, then we put the head on top and the tail below. So this is all that makes this graph. Okay, and the next task is again to find the type of the individual at the root here. That type should then, and actually does, follow the distribution omega t. And to do that, we proceed in 3 steps. So first we construct this graph without the types. Then we assign the types to the left of the graph by sampling a type for every line in an IID manner from the initial type distribution, and then we propagate the types forward by pecking and gluing, so exactly as we already know. And then that gives us this type today. And then we can also follow back the ancestral lines of every single site here. So ancestral sites have an underscore at the beginning, they are all ancestral, and here they split up into head and tail, and here they split up further into, no, where does it split? Here it splits further into head and tail, and so on and so forth. Lines that have no underscore are dashed because they don't carry any ancestral material. Okay, so that is it for this slide, I think. And then, yeah, let's start the recursion with omega 0. So that's the case where there is no recombination. So that's a pure branching process. So a simple Yule process at rate s. And let its line counting process be k. And it's well known that at time t, it has a geometric distribution with parameter e to the minus st. For those of you who attended the Frankfurt meeting 2 weeks ago, you may remember that Jason Schweinsberg had a beautiful graphical proof of this geometric distribution. It has expectation e to the plus st, and then it is simple to find the proportion of good guys at time t. So the probability to sample a good guy if you sample an individual from the population here. How do you get that? Well, now remember the pecking order, or the generalization of the pecking order tells you that this guy is bad if and only if all the KT lines in the past sample a bad guy. And yeah, that's what you have here. All the KT lines sample a bad guy. And yeah, that's the probability that this guy is bad, and then the probability that this guy is good is of course 1 minus this. And then it only takes a 2-line calculation to turn this into this simple and explicit expression. So, okay, and this leads us immediately to the law of X, which is then the start of our recursion. Why? Well, recall there's no recombination, so all the sides are glued together. So they are all glued, so the neutral sides are glued to the selected sides. So we can do the following. We can first decide which is the true ancestral line out of all these potential ancestral lines. And once more, something you in principle already know, but let me make it more explicit. We have arranged the lines here according to the hierarchy in the pecking order, so we can query lines one by one from bottom to top. So this one is bad, so this is not the parent. This one is bad, so it's not the parent. The next one is good, so it is the ancestor of this guy here. Okay, so altogether the probability to get a 0 at the selected site is, well, exactly the probability we had on the previous slide. The 1 minus the probability that they are all bad. Okay, and when I have found a good parent, then, since the others are just glued to it, the other sides are just glued to it, I sample the entire sequence corresponding, I sample the entire sequence from the initial type distribution conditional on the selected site being good, and quite the opposite, if they are all bad, then the ancestor is bad and the individual is bad, and then I sample from the initial type distribution conditional on the selected site being bad. And once more, these two lines are in a simple way turned into this simple expression, and that is exactly the solution of the pure selection equation which you've seen in the theorem. So that's your genealogical proof of the start of the recursion. Let us now, this I forgot to show. So once I've sampled the selected site, I sample from the initial distribution conditional on the selected site being good in this case, and this then gives you the complete sequence. So now we want to work up the recursion. Recall that omega k was the solution truncated at k, so with all recombination rates beyond k set to 0. So we need the corresponding graphical analog. So we need an ASRG k that is truncated at k. So we just make an ASRG where all recombination rates beyond k are set to 0. And then, we want to express omega k in terms of omega k minus 1, so we want to make a connection between the ASRG k and the ASRG k minus 1. So we want to couple the two. And the tool to do so is what we call the collapsed ASRGK, or CASRGK for short. That is an ASRG from the previous recursion decorated with ik squares at rate rho k on every line. So that's a mouthful, but it's simple. So here we have a situation with the selected site number 1, and then the black and white graph is the ASRG k-1, and then the collapsed ASRG k is the black and white structure with the 4 squares put on it at rate rho 4 on every line. And then we can turn this collapsed ASRG k into a full ASRG k by appending independent ASRG ks to each of the 4 squares. So they are attached here independently and they run for the remaining time. Now if you really do that for every 4 square, then the picture becomes quite untidy. That's why we like to work with this collapsed structure. It's very much like a menu which you can collapse and expand when you need it. Okay, and this now allows us to do the induction step. So, what do we want? We want to know the type x at the root of an ASRG k. That will then have law omega k. And we already know, by the induction hypothesis, we already know the type at the root of an ASRG k-1, so from the previous recursion. We call that y. And then it's clear that is the type at the root of this collapsed ASRG k if we ignore the 4 squares. That's clear because if we ignore the 4 squares, then it is an ASRG k-1, so the thing from the previous recursion. So we know that law. We know that law from the induction hypothesis. And then we do the following. We start here at the root and we follow back the ancestral line of the k-tail of this guy, which in this case is just the ancestral line of site 4. And since at this point we don't have recombination yet, that is also the ancestral line of site number 3. And then we follow that back until we meet the first 4 square. And let capital T be the time where that happens. And if there is no such 4 square on the ancestral line, then we set capital T to dead. But now let's assume there is such a 4 square. Then you expand here, you attach a new ASRG k here for the remaining time, little t minus capital T, and let curly z be the type at its root. And then what happens here is that, then recombination, so that means the head of this guy, sites 1 to 3, are combined with the tail of this guy, so this 1 here. So this 1 here replaces that 0 here, that's why this 0 is in brackets. And that then propagates forward into a 1 here and a 1 here. And this is why this x has a 0 at the last side where this x has a 1 here at the selected side where the y had a 0. So, that sounds good, but it doesn't help because this curly z comes from an ASRG k that has law omega k evaluated for the remaining time, but the law omega k is the one we wanted to find, so that sounds cyclical and we are not done yet. But we can do the same thing again and again. So in the ASRG k we have attached here, we can start from the collapsed ASRGK, then follow back the ancestral line of site 4 until you meet the first 4 square, then you attach another one, you follow back, and so on and so forth. So as indicated here, follow back, attach, expand, follow back, attach, expand, and so on and so forth. And the rest of the picture is summarized here into these dashed lines. And you do that until you attach an ASRGK that has no 4 square on its ancestral line. And then you have 1, because an ASRGK without a 4 square is actually an ASRGK minus 1 with law omega k minus 1, and that is the law we know from the induction hypothesis, from the previous step. And then it's clear what is happening. So 2 things can happen. Either there is no 4 square on that line, then x is simply y, because nothing has happened, or you have such a 4 square, let t tilde be the time where the last 4 square appears, and then you combine the head of y with the tail of z tilde, so z tilde is the type at the root of this graph at this point. So now you combine 2 things, the law of which you know, and this gives you immediately your solution in recursion k at time t, namely the law of the x. You decompose according to the last time t tilde, and then, well, if no 4 square has happened, then, well, the probability for that is of course e to the minus rho kt. And then you get the law from the previous iteration, and when a 4 square has happened, then you combine the head from the previous iteration, run for time t, you combine it independently with the tail from the previous iteration, run for the remaining time tau, and then all you have to think of is what is the distribution of the remaining time, but that is easy because of the symmetry of the Poisson process. So the time to the first event has the same distribution as the time after the last event, namely an exponential with parameter rho k. So you integrate against the density of that exponential and you are done. And this is exactly the result, the recursion I gave you in the theorem. So you now have your probabilistic proof via genealogies, and I could stop here, but I still have a couple of minutes, so I won't, because I think there's a number of people here well versed in dualities, and they will now wonder, where is the dual process? And in fact, yes, there is a dual process, and it is actually fairly simple. So let me recapitulate a bit and streamline and start at the very beginning and see whether we can tickle out the dual process. So again, let's take a situation where the selected site is number 1, and we want to start with a collapsed ASRG1. So a collapsed ASRG1 is an ASRG0 with 2 squares on it, but an ASRG0 is just an an ASRG0 is just an ASG because there is no recombination. So it's just a simple Yule branching process. That's the solid line here. And then you put 2 squares on it at their rate. Put the 2 squares on every line, sort of according to Poisson array. And then you follow back the ancestral line of site 2, which at this point is the ancestral line of site 1. and I let this be the lowest line. It could be any of the lines, but I found it easier to make the picture if it's the lowest line. So here I then attach an independent copy, a new copy of this C ASRG1 for the remaining time. That is now the dashed structure. Then I follow back until, again, the ancestral line of site 2, and again, for magical reasons, it is the lower line, until I meet the first 2 square, and then I attach another copy for the remaining time, and now it turns out that there is no more 2 square on it, so here I'm done and I stop. And then I realize something, namely, I've put on very many squares here, an independent Poisson process for every line segment. But then in the end, only very few of these squares are actually relevant, namely this one and this one. Always the first one on the ancestral line of the tail. And all the others are irrelevant. And that actually allows me to synchronize those squares. Rather than running an individual Poisson process on every line segment, I can run a single Poisson process for each of the ASGs. So one Poisson process for the solid one, another one for the dashed one, and so on and so forth. And then when a point falls, I draw a bar across all lines in that graph. Meaning I have sort of synchronized these points, and I'm allowed to do that because, as I said, only one of these squares is relevant. So I do actually not need the independence across lines. What I need is the identical distribution across lines, but I don't need the independence, and that's why I'm allowed to synchronize. And then I have the convention that sort of the new copy attached below, that will then actually go to whichever of these 2 lines is the true ancestral line. So if this one is the true ancestral line, it will be attached here. That again can be done because of the because I don't need the independence across lines. And then I can label and prune the graph. And with that I mean that I label every line with a set of sites to which it is potentially ancestral. So here I have green, blue, and red for site 1, 2, and 3. And then we need a 2 bar, and that means that the green head is separated from the blue-green tail. And yeah, and then I see that I can actually remove some of the bars. So here is another 2 bar, but the green line is in the head of this, so no further splitting can take place. The splitting has already taken place here, so I don't need that. I remove that kind of bars. And let me also know that when a bar falls on a set of lines that is all contained in the tail of that bar, then again no split happens, right? So no lines continue to the left, and a new copy is attached below. So that has colors, that is already a bit nicer. And we can then iterate this by putting on 3 bars and so on and so forth. And of course the same labeling and pruning all the time. Okay, and this leads us to the Yule process. So the Yule process is a weighted partitioning process, sigma t vt. And sigma t is the pure partitioning process, so that is the simple splitting of lines. Well, just imagine there being no branching. Then you just see the splitting, and that is the sigma t. And then the vt assigns an integer to every part of every partition, and that is simply the number of lines currently present in that block. So at this time point, for example, the partition is green and blue-red, and the weight for the green is 2 because we have 2 lines, and the weight for the blue-red is 1 because there's only 1 line. So that is the process. More precisely, if the current state is partition A and weight vector B, partition A with blocks A1 to AM, then 3 things can happen. First, every block, say AJ, can split into an I head part and an I tail part, and that happens at rate row I whenever this is a true split. So I do not mean cases where the block is completely contained in the head or a tail, and completely contained in the head or the tail. I want to see true splits. And when that happens, then the head part walks away with the weight of the block, the previous block AJ, and the tail part starts again at rate 1, with weight 1. So this is exactly what we see here, right? The headlines, they just go through, they are not affected, and the tail just starts again with a single copy attached below. And then independently of all the partitioning, the weights perform independent Yule processes. So every line branches at rate S, that is exactly, the branching part of the process. And then finally, every weight is reset to 1 whenever a bar appears where the block is completely contained in the tail. So, like here. Here you just restart at 1 and nothing else happens. So, that's my Yule process. And this now allows me to write down the duality function, H, applied to partition A and weight vector V and probability measure U. And that does the following. For every part of the partition, I first decide whether the type at the root of an ASG with VA lines is good or bad, and then I sample the type of the subsequence corresponding to A from the corresponding marginal measure, conditional on the selected site being bad or good. And then the theorem tells us that this duality function does what it is supposed to do, namely it makes the weighted partitioning process into the dual of the solution of the differential equation. This left-hand side is actually deterministic because we've taken the deterministic limit, and in particular we can write the solution of the differential equation as the expectation of the duality function with the weighted partitioning process started in the coarsest partition with just a single line. Okay, and that is it, and thanks for listening.